Right, this is very weird doing this, but I thought I would do a bit of an online lesson for you. So what we're doing today is we're going to differentiate y equals e to the x. If you remember, if you worked through the last lesson at home, then you were sketching some graphs, sketching some exponential graphs, seeing what they look like. So we're going to go on from that, rather than doing things like 2 to the power x, 3 to the power x, that kind of thing. We're going to look at this special number e and what's so special about it. So where it fits in the sequence of lessons, that's what you did last time. So we're going to look at what its graph looks like, why e is such a special letter, and then also how we can differentiate that as a function, because it's sort of matched and tied in with what's so special about e. Okay, so just a little thing to start with now, just to warm you up a bit. So I've got a number of different graphs here, and I've got a number of different functions here. So if you just sort of take a moment to have a look at those, you can see we've got two distinct types. We've got ones that go from very small values up here to very big values here. So hopefully, well, there's 3 of those and 3 of these, but hopefully you'll realise that when I've got an integer raised to a power, or a number bigger than 1 raised to a power, as I increase the power, then it gets big, and it gets big very quickly. So that's going to be your whole thing about your exponential functions, your exponential growth. So if I was to match those 3 with these 3, hopefully you're starting to think, okay, well, the one that gets biggest the fastest, okay, is going to be the biggest base number. So that's going to be your y equals 4 to the x. Okay. The one sort of in the middle is going to be your y equals 3 to the x, and then your 1 still has exponential growth, but just not as rapidly as the others because of the base number. Now what's also interesting for you to kind of appreciate is what happens the other side of the y-axis here. What you'll notice there is that the 2 to the x1 has bigger values than the 4 to the x1 when your indices are negative. And if you think about why that is, when you've got a negative power, that's the reciprocal of that. Okay, so when you've got your negative power, this is going to be a half raised to the power, this is going to be a third raised to the power, this is a quarter raised to the power. So that will get smaller quicker than that one. Okay, so you can tie it in with that. Now that ties in quite nicely with these 2 that we've got here. These are the ones that are fractions as your base, and if you think as the power gets bigger and more positive, then they're going to get smaller. But when you have a negative power, remember, again, that's going to be the reciprocal, so you're going to take that, and that's equivalent to like your 2 to the x or your 3 to the x. Okay, so when we have a look at these, the one that's going to get biggest, that's going to get smallest the quickest, okay, is the one that's got the smallest power. So that's going to be your the smallest base, sorry, that's going to be your 1 over 3 to the x, okay, and that is going to be your half to the x. Okay, and again, notice that when you get into these powers, they sort of switch over which one's on top and which one's on the bottom. Now this highlights quite nicely something that's special about this number e that I'm going to introduce you to in a sec. If you were to draw these graphs accurately, these ones here, and you were to draw a tangent to the graph there at x equals 0, what you would find is that the gradient of this graph is just a little bit less than 1, okay, whereas the gradient of this graph is just a little bit more than 1. So what that implies to you then is that there will be a value somewhere between these 2 where the gradient of the graph when x is 0 is exactly 1. And that's basically your letter e, okay, or the value e. So if you were to draw the graph y equals e to the x, it would look very similar to the other ones. Notice they always go through at 1 there, okay, because anything to the power 0 is 1. But what's special about e is that if you were to draw a tangent here, then the gradient of that tangent is exactly equal to 1. Now its value is 2.718, and then it carries on. There is a button on your calculator, so if you grab your calculator, if you press the red alpha button and then the times 10 to the x button, you'll see just above it, it has a number e. So if you press that, so press your alpha and then that, it shows you e is 2.718281828, etc. That's the number of places on your calculator. So if you're ever asked to use the value of e, that's e itself. There is also an e to the power 1, which is basically over just below the x1. You need to do shift and then the lun button, and that's got e to a little power. Okay. Right, so what's special about this is because the gradient of the function is 1 here, what that means is when you differentiate e to the x, you get e to the x. So it basically stays the same, okay? And this is to do with, in nature or in the real world, when you have things that are either exponentially growing or exponentially decaying, then the base number indicates the speed at which they grow or decay, and e is actually something that occurs a lot in nature, so you get a lot of exponential growth and decay that happens with this as its base number. Okay, right, so let's have a look at the differentiation now then. Okay, so we've already mentioned that if I've just got the function e to the x, when I differentiate it, it stays as e to the x. These just show you the different notation. If you remember with your differentiation notation that you did with your other teacher, if you've got f of x equals, then you do f dash x equals. If you've got y equals, then you do dy dx equals. Now, sometimes we will get exponential functions that have a little bit more of a complicated power at the top there. So what you've got to remember is if you've got e to the power of something times x, when you differentiate, basically you differentiate the power, okay? So if it was 5x, you would get 5e to the 5x. Notice, this bit's important, whatever this is here in the thing you're differentiating, that must stay the same. So you do not change the power at all. All you end up with is you end up with that times by a k at the front. And again, this is just repeating the same thing, but just in that different notation. So make sure that when you differentiate something like e to the, say, e to the half x, you would end up with half e, but also to the half x. So do not change that power when you're differentiating. Okay, right, let's just do a couple of those together to make sure you're happy with that then. Okay, so y equals e to the power 4x. All right, so all of these are y equals. So for my differentiation notation, when you do ones from the book, make sure you write it out and then you write dy dx. So very important, do not change the power of it. Okay, e to the 4x stays as e to the 4x, but then you get times by an extra 4 at the front. Now this is to do with something called the chain rule that you will do more of in your year 13 when you do your differentiation in there. So when this comes up in year 13, you'll sort of realise, oh yes, that's used in the chain rule. Okay, same for this one. Do remember, you leave that exactly the same, that doesn't change. All you do is you times by the differential of the power or the number in front of the x for these ones. And careful with this last one. Okay, it's already got a 3 at the front. All right, so I'm going to leave my e to the 2x exactly the same. By my rule, I would times it by 2. I've already got a 3, so that would give me a 6. Okay, so do make sure that you leave the e to the power thing exactly the same. Okay, final thing then, let's have a look at some graphs and some graph transformations. You remember you did transformations with me, so there were a few different transformations. There were some stretches, there were some translations, and then we also did some reflections in the axes as well. So if I had the graph y, if I started with the graph y equals e to the x, and I said to you, what would the graph y equals e to the 2x look like? Okay, it would be very similar to it. Okay, it would still go through the y-axis at the same point. If I think back to my graph transformations, what's happened here is my x from my e to the x has been replaced by a 2x. And if you think back to our graph transformations, when we replaced the x with something else, that ended up being a stretch in the x direction, okay? But remember, when it's x replaced by something else, a little bit more complicated in that it's not a stretch scale factor 2, it's a stretch scale factor 1/2 or a half, okay? So if I was to draw it, okay, this is what I would draw it like. If the asymptotes, I haven't really mentioned asymptotes actually, with your exponential graphs, that will tend to 0 here. Now this is zoomed out quite a lot, so it looks like it hits 0, but it doesn't. This axis here is an asymptote, and that curve is tending towards that. Now, when you're sketching graphs, you need to make sure you draw on your asymptotes, especially if they've ended up being moved to a different place, okay? So y=0 is an asymptote, state that, goes through at 1 here, but it pretty much has a very similar shape to your e to the x curve. So let's look at one that's a little bit different then. y=10 e to the minus x. Okay, so we've got two things going on there. The first thing, if you look at the power, my x has been replaced by minus x. Okay, my x has been replaced by minus x. Now, if you remember back to your graph transformations, that is a reflection. Okay, so what it is saying is, say if I had a value in my original graph plotted where x is 2, that value would be plotted instead where x is minus 2. So that's a reflection in your y-axis. What does a times by 10 do? Well, think about it. Times by 10 is timesing all of the y coordinates by 10, so that is going to take it and stretch it in the direction of the y-axis by a scale factor 10. Okay, so two things going on there. Reflection, I've written over there, so reflection in the y-axis and a stretch parallel to the y-axis with scale factor 10. My asymptote hasn't moved for this one. All right, so I would still state that y=0, or the x-axis is an asymptote. So if I was to draw it, you'd see we've got our negative power here. So this is representing exponential decay, so something that starts with a big value and then goes up. Notice though, the difference with this one, where it goes through on the y-axis, because of that times by 10, the stretch in the y-axis has meant that where it went through at 1, it now goes through at 10. Makes sense. If I put x is 0, I get e to the 0, which is 1, and 1 times 10 gives me my 10. Okay, one last one which has quite a lot going on here. Okay, so with this one, a number of different things. So let's just have a look at what we've got here. We've got the power here. X has become half x. So remember what that means. That's going to be a stretch in the x direction, okay, but it's going to be scale factor 1/2 or scale factor 2. What have we got here? We've got a times by 4. So the y coordinates times in by 4, so that's going to be a stretch scale factor 4 in the y direction. Now this is a slightly different one. Here I am adding 3 to it. So if you think about what adding 3 to the y coordinate does, it takes your graph and it moves it up 3. Proper term is a translation. Remember how we define translations as a vector movement in the x direction over movement in the y direction. Okay, so these are all of our things going on here, 3 things. Scale factor 2 parallel to the x-axis, that's that bit. Okay, stretch parallel to the y-axis, scale factor 4, that's that times by 4. And then the +3 is a translation, 0 in the x direction and +3 in the y direction. So this one, notice the asymptote has moved because of the +3 part. So when I'm going to sketch that graph, do make sure if your asymptote isn't on the axis, then just dash it in there. You probably put a 3 there. Okay, not particularly amazingly good to scale, but that's going to be 7 there. Reason being, if I put in x is 0, e to the 0 is 1, 1 times 4 plus 3. So you'd be expected to mark where that goes through the axis as well. I mean, the times by 4, the shape of it stays the same, okay? If you were to draw it, you know, sort of without the 4 there, then it wouldn't go up so high and it would go through a different place there. So make sure when you are sketching your graphs, think about these transformations, think about labelling your asymptotes and drawing your asymptotes in, and make sure that you show nice and clearly where it goes through on the y-axis. Okay, right, over to you then. So these are the questions, exercise 14b. There's a couple of different sorts of questions. One of them says draw an accurate graph and then measure some gradients. So for that one, plot values on your squared paper, make sure it's nice and accurate so you can draw your tangents on to measure the gradient. A sketch should be similar to that one that we've just shown, so something like this. If you've got your asymptote like that, if it's going like that, mark where that goes through on the y-axis and label where your asymptote is. Okay, so just think carefully about those. Okay, so that's that. So something for you to get on with. It's been a very quiet class without you all. Hope you're all well. Do look after yourselves, and I'll see you again soon. Thank you.